Hello and welcome for the day 4 at the OPC Day International 2022. Before I start and introduce all the speakers for today, I like to recap shortly what happened already this week so you have a chance to also see that videos. On day 1, we had a lot of keynote speeches on different areas on the biggest challenge for us human beings to save the planet. It was all about the energy transformation. On day 2, we had a deep dive into the OPC UA technology, on the one hand on security topics, but also on how to scale from edge to cloud and how OPC UA is extending down to the field level. The day 3 was about all the promise about semantic, secured industrial interoperability. So the key was the semantic, and we had a lot of collaboration partners where the OPC Foundation with more than 60 groups are defining the semantic to have standardized information models. We also announced new groups here. It was an amazing day. Just have a look what's happening on day 5. And this is where we thought we got so many questions. Why not try to address them in easy, short videos about 5 minutes to 10 minutes and let people explain how to solve it with OPC UA technology. But today it's the day 4. And the day 4 is that we get an introduction from Jim Luth, the CTO of the OPC Foundation, talking about OPC UA systems, which means we are not talking about two OPC UA components, a client and a server, or a publisher and a subscriber. Instead, how to scale into large systems, how to connect dozens, 100,000 devices, how to take care, how to handle security certificates and so on. After that, we talk about MQTT, and Erich Barnstedt from Microsoft will give us an introduction. How does things fit together? Where should I use OPC UA? How does it relate to MQTT? And how is it handled with the asset administration shell? Erich Barnstedt will also continue and talking about the OPC UA Cloud Library, because he initiated this topic some time ago. It has been released already last year in 2021. And so this functionality is also available as commercial products meanwhile, and that's why Jonathan Malessa from Inray is also joining this talk and helping here to present. We will have again Espen Krogh here from Prediktor, because we have two great end-user success stories. Espen will talk about OPC UA in the world's largest solar panel farm and the world's largest wind turbine park, and obviously we are proud that OPC UA somehow plays a role here, and we like to learn more. And after that, we also like to get a presentation from Mariatou from L'Oreal, how OPC UA helped on the digital solutions inside L'Oreal to increase operational performance. With this, I like to say thank you again for joining here. Have a good day, and let's start.
Hi everyone, welcome to OPC Day. It's a pleasure for me to be here to speak today. My name is Jim Luth. I am a system architect for process automation R&D working for Schneider Electric, and I'm also the CTO of the OPC Foundation, where I also chair the OPC UA Working Group, a member of the TAC and the Technical Control Board. Today I'm going to talk about OPC UA systems and what I mean by systems as opposed to OPC UA components. So let's get into it. So in today's sessions, I will talk about what I mean by UA components and how that differs from what I mean by UA systems and how they're related. And we'll talk about global services, that is, services in an OPC UA system that have an advantage to be centralized. and most of my focus will be on what component authors need to do to take advantage of these optional global services. After we've discussed the services themselves and why you might use them and the advantage of having them centralized, I'll let you know where to find more information should you want to write a component that avails itself to these services, or if you want to write a central component to be the service itself. So by UA components, what I'm talking about are the UA clients and servers and sometimes publishers and subscribers that make up the applications in an OPC UA system. Any collection of such components in a particular place to do a particular task would be considered an OPC UA system. These OPC UA components are known in this OPC UA specifications as UA applications. I use the term components and applications here synonymously. The required behavior implied by the OPC UA specification largely centers around the interactions between these components, and hence OPC UA can be considered a decentralized architecture that doesn't rely on any centralized components. So this decentralized concept allows very small OPC UA systems to work easily without any burden of decentralized components. So as an example, let's assume that my OPC UA system consists of just this one OPC UA server, and I want to provide user access control to multiple clients that may be interacting with me. In a system like this, it's reasonable that the OPC UA server would store and maintain the username and passwords for all of the potential users of my server, and each time the check for the user and password would be done by the server. But if instead my UA system consisted of many servers and many clients and many publishers and many subscribers, that same system would be difficult to maintain without the use of some centralized components. So again, using the example of each server storing its own username and passwords for the same users becomes a maintenance nightmare for an administrator who has to keep everything in sync, adding and removing users, updating passwords, and so forth. So it's for this reason that we introduced the optional centralized components to aid in largely in the administration of OPC UA systems. So the first central concept we should talk about for OPC UA is the notion of discovery. Discovery allows one OPC UA application or component to discover other OPC UA components in the same system. Again, we use the term central or the notion of a system here to talk about the scope of discovery, and we're talking about, in this case, clients and servers discovering each other, or publishers discovering subscribers, or vice versa. The point here is that the concept of discovery is a global one. However, the default and provided mechanism for discovery that all OPC UA servers and clients must use is actually a decentralized, what we call ad hoc discovery mechanism. So this ad hoc discovery mechanism requires actually no centralized components, and instead relies on local components and some multicast DNS to synchronize the different local components, such that a system-wide, or at least in some cases a subnet-wide, discovery can occur. The ad hoc nature of the discovery has its advantages. Of course, having no central infrastructure or component required is a major one, but there are some limitations. In particular, we'll find that the broadcast messages used in multicast DNS don't always travel as far as you would like them to in the network, and there are some security implications. So OPC introduces the concept of a global directory service to overcome some of the limitations of the ad hoc discovery mechanisms. And in this case, the GDS, which can stand for Global Directory Service, or it can also imply a global directory server, that is a central server that runs the global directory service. And the GDS is really meant to be a centralized component where there are one or sometimes a few of them chained together in various ways, but nonetheless a centralized component that is in fact itself a full OPC UA server. And that is, it has a fully viewable address space, and it will read, write, and browse nodes and so forth, just like any other OPC UA server. But it has a specific information model with a specific object type called directory type, which in turn has its own set of methods, and these methods are used for doing directory type things. And it's the use of these services that imply that a client, be it a OPC UA server or an OPC UA client, that can take advantages of the features of the GDS itself. So let's take a look at the case of a GDS being used for server administration. For an OPC UA server to become known to the central GDS, the server itself needs to be registered with that GDS. And this starts to bring up one of the first advantages to using a GDS. That is, in the central server, every registered application has been validated by an administrator. So here, instead of seeing the OPC UA server register with the discovery server, as it does with the LDS in the ad hoc case, we see a server administrator using oftentimes a separate administration app to register on behalf of the OPC UA server the registration for the server. So again, one advantage to using the GDS in this case is that it's a trusted source for discovery as opposed to an ad hoc, somewhat untrusted source. So typically, of course, the server registration will happen during setup at some point in time, and that registration, of course, requires security of this server admin to allow this registration to occur. So clients use discovery servers, or the central discovery server, more or less for the same reason it would use the decentralized discovery mechanism, and that is to find registered servers in the system. But in the case of the central server, the client discovery mechanism uses a different method call, in this case query servers, to find the servers that it's interested in. And the query servers takes a different type of filter string than the typical server discovery with the ad hoc case. And thus the important thing to understand is a UA client, while it requires to use ad hoc discovery, it does not require the use of the central discovery server. So to use the central discovery server, the UA client has to be written specifically to do so. And again, this is where the ability to use these centralized components becomes important, not just for people that write the centralized components, but for every OPC UA application developer, so that they understand that where these services are and why they would want to use them. So one of the interesting chicken and egg problems that arises for clients wishing to use a GDS is, how does the client find the GDS itself? And there are several mechanisms that can be used to aid in the discovery. One of the classics is that a good client would be able to be configured with the absolute address of a central GDS to be used, and therefore it's a manual configuration, typically of one endpoint for the one centralized GDS. However, a clever use of the ad hoc discovery mechanism in conjunction with the central server actually allows an alternate where the client discovery mechanism will first use the ad hoc discovery to find any available GDSs, and once it discovers GDSs, it through the ad hoc mechanism, it will connect to the GDSs directly and then query those servers. Query the GDS for the list of all other OPC UA servers. So again, in the case of discovery, OPC UA provides multiple mechanisms, and in many cases they can be chained together. So let's move on to our next centralized service, certificate management. As you probably know, OPC UA is heavily based on PKI, public key infrastructure, that is the use of X509 certificates that are used to identify both OPC UA servers and OPC UA clients. Since each OPC UA server instance and each OPC UA client instance in a system, of which of course there can be many, requires its own unique certificate, and certificates by their nature of how they're designed do not last forever, managing and updating and keeping the certificates correct in each of the clients and servers is a useful thing to do in a centralized manner. So in OPC UA, we've introduced the ability to have a centralized service, in this case the certificate management service of the GDS, and have it be responsible for managing the certificates for all the OPC UA applications. OPC UA interfaces are used between the GDS and the clients and servers in two different directions. A typical scenario is an OPC UA client will connect to a GDS and will pull its certificate from the GDS, because again, the client is the initiator of the communication and initiates, in this case, the pull action. A server, on the other hand, is a listening for connections, and in this case, the GDS acts as the client and often will push the certificate to the actual OPC server. And of course, in some cases, you can choose to use the other model if you have the reverse interface available to you either way. And it's not just the initial certificate that's managed by the central administration here. The certificate renewal is managed so that when the certificate is about to expire, the client will pull and get a new certificate when it's ready, when the certificate is ready, the central certificate manager will push the new renewed certificate to the server. Additionally, the revocation lists that are necessary in order to properly do PKI when you have a certificate authority involved also need to be kept fresh and updated in the applications, and the certificate revocation lists are also managed in the same way, both with the push and the pull model. And lastly, the trust list. That is the list of certificates that a client should trust from servers, and the list of certificates from the clients that the server should trust in authorization and connection activities can be managed through the central administration of certificate management. So in all these cases, as with the previous discussion about the GDS, for a client or a server to use the central administration for certificate management, it has to be built with that capability involved. We don't mandate the use of certificate management this way. Vendors can choose to implement certificate management however they want in OPC UA applications. However, it's strongly recommended that this mechanism using the certificate management interfaces of the GDS are used for this purpose. So the next key service that I want to talk about that's centralized is the key credential service. And first, let's talk about what a key credential is. So a key credential is a fancy name for a combination of a unique identifier and a secret that's used to access some service. A reasonable example of a key credential is a username and password. We're all familiar with those. But there are other fancier types of key credentials that aren't considered usernames and passwords, but they all involve an ID and a secret, and that's what we're talking about managing here. Where these come to be used in OPC UA, they can be used and managed in OPC UA for anything, but a typical example of where they're used is to access an authorization service, and we'll talk about authorization services a little bit later today, or a broker, i.e. an MQTT broker. So in PubSub, where we use MQTT as the middleware for the publishing, typically any entity that's going to access that broker, the broker service itself is secured, and the broker service will require some key credential to be passed to it in order to use it, and therefore the OPC publisher or subscriber would need to know that key credential. So by centralizing the management of the key credentials, again, I can update them and revise them and change them and present them and so forth in a centralized manner. So as you can see, the picture of the key credential management looks strikingly similar to the certificate management, and in fact there's a lot of parallels here. We have a push and a pull model, so clients typically will pull their key credentials from the central administration, and servers will typically have the key credentials for them pushed to them. And again, these are all managed it can be managed in a central location through the GDS, and can be fine-grained control over which particular applications get which particular credentials pulled or pushed to them. So the next centralized service I want to talk about is authorization services. And the authorization services are a way to separate concerns such that it allows OPC UA applications to delegate the user authentication and user management and assignment of users to roles to some external entity. And again, for example, an OAuth 2 server. And this decoupling makes it easier for administrators to manage users coming and going on the system, users' roles changing on the system without having to go to each and every OPC UA application and making changes based on those types of personnel changes. And this service, these services are also used, and I'll explain in a further slide how this might look, but we actually achieve a single sign-on in OPC UA systems. So let's take a look at the workflow for authorization. And I'm going to start in the middle here just to confuse you. But let's suppose a client here wants to read a value from a node in some OPC UA server. But that node and the value it wants to read is controlled with access control, and only certain people that are in certain roles are going to be allowed to access that particular value. So what has to happen in the flow here is the client effectively connects to the centralized authorization service and presents its user identity token, whatever that is. It could be a username and a password. It could be something else that it already has. We'll talk about that in a minute. And with that user identity token, the authorization service will check the mapping rules that it has or that some underlying system might have, and come up with an access token. And the access token is not too much different than the user identity token, except it very explicitly has the list of roles that are required or that are granted to that user based on what roles, knowledge of the roles the server will accept. Once it has that token, it will in turn use that token in its connection to the server and present that to the server and tell the server, I'm this user and these are the tokens I've been granted. At this point, the server will take the access tokens, validate them with the authorization service to be sure that the tokens are correct and real and make sense given the system. And then from the roles presented in the token, it will determine whether this node and the value and whatever operation is being done on that node is valid for that role. Okay, and so all these pieces here have to come to play, but at this point, the management of which users are in which role is not of concern to the server. All the server has to do is know which permissions he's assigned to the role to access the node. So again, the separation of concerns between what do I do in my controlled device with information, in this case the server, and what do I do globally in a system-wide basis in the authorization service. So let me explain now how this authorization service might be used in a more concrete example to provide the single sign-on that I said we could provide with this. So let's make the assumption in this case that we have a client, an OPC client that is running on Windows, and that Windows machine is in a domain, and the domain has Active Directory installed, and my GDS uses Active Directory as the authorization service, the back end of the authorization service. The GDS is the OPC UA component, the centralized component that's running the authorization service that's used as an intermediary so that the client and the server can talk to the GDS using OPC UA mechanisms, and they're shielded from the specific backend APIs for Active Directory. So in this case, the single sign-on happens quite nicely because the client, when the client before even the client starts up, the Windows machine has been started and the user, an Active Directory user, has logged into the machine. And so the user identity token that I need for this client is already present. So this step doesn't per se really happen. The client already has the user identity token that he needs because the machine has already been logged into by the user. So that token is passed to the authorization service, which in turn talks to Active Directory to get the roles that were assigned to that particular user, creating the access token with the roles. The client that takes the access with the token to the roles, the server collects those and then can make that assignment. So all of this happens without any server storing username and passwords, nobody having to log into the client application, the UA application, separate from the Windows login to the UA application, and essentially single sign-on is achieved in all of the clients and servers in the entire OPC UA system in this case. While I'm here, let me point out another common use in systems of the way that the services in a GDS are architected. The use here of a GDS and the authorization service as an intermediary between the OPC applications and the actual backend doing the work is a common theme. So in this case, I've used Active Directory as the OAuth2 service providing the authorization on behalf of the GDS. The same thing is true, though, with certificate management. As an example, a CA and the services of a CA, a certificate authority, are often used as a separate back end to do the work of the GDS, as opposed to the GDS actually being the certificate manager. It's really just a go-between between a real certificate manager and the OPC UA applications. And the same can be true of any of the services provided by the GDS. The GDS may in fact just simply be an intermediary, and the real work is done in a separate subsystem. Another centralized concept recently developed for OPC UA is the notion of alias names. Through this mechanism, we allow a node in an OPC UA server to be associated with a user-defined name called an alias name. This alias name can then be used to look up the actual node, the ID or the address, if you will, on a system-wide basis. And this works much like a DNS server is used to resolve a domain name to an IP address. In our case, an alias server resolves an alias name to a node in an OPC UA server. So these names, as I said, are user defined. And again, a good example of that in process systems, typically on a PNID drawing, you'll see symbols like this. And this particular level controller here has been given a quote-unquote tag name called LIC 135. And although that doesn't seem very descriptive, throughout the plant, and no matter who you're talking to, LIC 135 uniquely identifies this instance of this controller in this loop. And so it would be common that the tag name or the alias name for the tag is given the name LIC 135. But of course, it corresponds to some node with some node ID in an OPC UA server that otherwise wouldn't be able to be identified as LIC 135. So when the alias names feature is implemented centrally in a GDS, the registration of those alias names, the tag names and so forth, from the underlying system can be done in several ways. The simplest way is that an administrator could configure a tag name directly in the GDS and then provide the link to the server endpoint and the node ID associated with that tag. So sort of the manual, I can configure the GDS to contain any tag name I need it to contain. However, there's another way to get the tag names to the GDS, and this again comes from the idea that the GDS is the central thing that all the servers register to. So the logic is that when a server registers with a GDS, the GDS can go to that server and periodically read and refresh its list of alias names that are already defined in the server itself. So the tree here of the nodes in the server are then combined and coalesced into the tree of alias names in the GDS. So the idea is now that each server could have its own locally assigned tag names that are available. So if I connect directly to the server, I can find the tags in its server, but separately or in addition, I can go to the global service here in the GDS, and here I can resolve all tag names in all of the servers in the system, and which of course is typically how clients will prefer to use it. So you go to the top level alias server. In this case, of course, the GDS is to be considered the top level server, and from there I can do the queries and the resolution to resolve my tag names to find my actual nodes in the OPC servers. You'll notice here in the diagram we have more than just tag names shown, and the alias name concept can be used for things beyond tags and sort of the named nodes in OPC servers. One example of that is in PubSub. We use it to provide named topics for PubSub publishing and subscribing. So again, a similar feature where I may not know where I can get certain data, but I know what the data is called. And so if I know that I'm supposed to subscribe to boiler data, I can go look up the topic called boiler data, and now I get the information I need as to what I need to subscribe to receive that boiler data without knowing anything about the absolute locations, IP addresses, etc., of the publishers that might be sending out boiler data. And as with the previous services that we've looked at, clients and servers, publishers and subscribers, any of the OPC UA applications that want to make use of the alias name feature, they need to actually write code to support that. So a server would need to allow alias name assignments. Again, these are end user typically installed name assignments. These aren't something a vendor would use to assign names ahead of time. Typically their assignment is made by the end user, so the whole configuration of that would have to be supported. And of course you'd have to be able to support the tree that I showed in the previous slide with the alias names and the grouped appropriately so that other clients and the GDS could update themselves with those alias names. Similarly, for a client to make use of alias names in the typical way it would do that. So as you can imagine today, when a client browses a node ID in a server and finds, usually with the user interface and the help of a human, the client will find the node of interest, and then it will save that, persist it, so that when it starts up at a later time, it knows to just connect to that server, read that node, subscribe to that node, and get the value. So normally a client will persist the endpoint and the node ID, or sometimes the endpoint and the browse path, in order to start up again and get back to where you were. I want to subscribe to the 5 things I'm interested in. I have to remember what those 5 things are, and usually what I'm remembering and persisting is the endpoint and node ID and or the endpoint browse path. In the case of using alias name, though, you don't persist either of those. The logic is I persist the alias name, right? The alias name is the name that's been given to in the system, and I use the alias name to look up the endpoint and node ID each time when I go to connect, or each time that it might have changed. And there's also ways to register to learn when an alias name changes or its assignment changes. And so this whole mechanism to properly use alias names, again, doesn't come for free in OPC UA. The clients need to be written to actually make use of it. And the last centralized component that I want to talk about today is the security key server. So the security key server is an entity that's used strictly in the pub/sub paradigm for OPC UA, and it's used to manage the keys used for signing and encrypting the messages sent from publishers to subscribers. And in OPC UA, the keys used for this are not the same types of keys that are used in the PKI for client server, in that they are shared keys and they're temporary. And by temporary, I mean each key is used for anywhere from a few minutes to a few hours temporary. So to keep a flow going between a publisher and a subscriber, the keys change in every few minutes or every few hours, and the publishers and subscribers need to be using the current and correct key. And to do that, both the subscribers and the publishers need to be in relatively constant communication with the security key server to obtain the latest set of keys. So this particular service can be implemented anywhere. It's often implemented directly in a publisher, such that you might not even think of the security key server as a centralized component, but that would be a mistake because it can be. But oftentimes a publisher will manage its own keys, so to speak. So the subscribers talk to the security key server in the publisher to renew their keys. But there are advantages to implementing the security key server as a central component as opposed to in the publisher. In particular, it allows a key to be used and managed in one place and be used by multiple publishers. And this can be an important feature in some organizations of publishers and subscribers. So this service again is one that the good news here is PubSub is set up in a way that when you attempt to find the security key server and the location of it, it's pretty much directs you to its location no matter where it is. But I didn't want to leave, so this one maybe is the only one you could say comes for free, as in when you're using the security key server, you almost don't have to do anything special to use a centralized security key server. But it is certainly important to understand that a GDS as an entity may easily be the system-wide security key server for a group of publishers and subscribers, and it's important to know that too is an example of a service that can be centralized. So as promised, I want to point you in the right direction to find more information about the centralized services I've talked about today. Hopefully, you'll consider building your OPC UA applications to use these services. I hope if you've already built OPC applications that don't use these services, you'll reconsider going back and enhancing your products to make use of these. The first four services we talked about, discovery, certificate management, key credential management, and authorization services, are actually described in a standard OPC 10,000-12, or what we refer to as Part 12 of the specification, discovery and global services. So that one should be easy to find. It has the word global services directly in it. And so that's most of what I talked about today, but not everything. The other two, alias names, has its own part. It's called Part 17, alias names. And there you'll find all the requirements for clients and servers to use alias names, plus how it's aggregated up into the global discovery server. And lastly, the security key service, as I said, is used strictly for PubSub, and that whole service and how it works is defined and described in the Part 14 PubSub part. Oh, and another way to get more information on some of the global services I talked about and introduced you to today is to attend tomorrow's OPC Day sessions, where our how-tos go into more depth on some topics, including some of them that you heard about here today. So thank you very much for joining me. I hope I've invigorated your desire to go and enhance existing OPC UA applications or write new ones that make full use of our global services.
Thank you very much, Jim. We appreciate it to get that short, comprehensive, precisely explanation from you as a CTO of the OPC Foundation. Perfect. The next speaker is Erich Barnstedt from Microsoft, and he is giving us an overview on how does things fit together with OPC UA. Is it just a last mile? Does it scale to cloud? How is it related to other technologies like the asset administration shell? Is the asset administration shell the same as a digital twin, and whatever? Erich should be online. Yes, I see you, Erich, and it's your floor, Erich.
Okay, perfect. So welcome everyone. My name is Erich Barnstedt. I'm the Chief Architect for Standards and Consortia at Microsoft in the Azure IoT team. And today I want to talk a little bit about some of the articles online that you may have read about OPC UA versus MQTT, which is best, OPC UA versus the asset admin shell, which is best. and then figuring out how we can untangle this mess. So first of all, let me start by saying there is no OPC UA versus MQTT. So what happened is a bunch of companies that weren't aware of OPC UA pops up, and that OPC UA pops up leverages MQTT, came up with alternative technology, and then felt compelled to write articles comparing OPC UA and MQTT, and didn't realize that there's actually a mapping defined in OPC UA actually leverages MQTT. So any articles that you find in relation to that, you can just ignore. And then there was a technology built by a number of companies in the US called Sparkplug-B, and we need to talk about Sparkplug-B a little bit, because again, there's a lot of alternative facts, let's call them, online that we need to clarify, and I'll attempt to do that with this slide. So first of all, a lot of times you read that the Sparkplug-B standard, it's not a standard, right? It's a proprietary extension to MQTT. That doesn't make it a standard. MQTT is the standard. If you create an extension to it, you don't automatically become a standard. You have to go through the normal standardization process, just like OPC UA did many years ago. The other issue really with protobuf is that it uses, with Sparkplug, is that it uses protobuf payload invented by Google. And surprise, surprise, that's not supported in either AWS or Azure, which means that you need to translate the data in the cloud. Now, you might think, what's the big deal? Well, once you start using the cloud at scale, it becomes a really big deal, because you have to pay for that data conversion. That data conversion becomes a real, compute overhead when you're using the cloud, with many, many different assets connected to it, and it adds no value. So you're much better off using a payload like JSON, for example, that all cloud services natively support, so you don't have to convert the data again in the cloud. And then another thing is, converting the data on the shop floor is also required, because obviously a lot of times, data comes from all sorts of different machines. So you're converting it to OPC UA, or in the case of Sparkplug-B, you may be converting it from OPC UA. Well, that conversion is not defined, right? So there's no mapping from OPC UA to Sparkplug, which means that any implementation will be different, and usually, again, well, not usually, always proprietary. It's going to lock you into that particular data format and completely undermines the whole idea of multi-vendor interoperability, which is the goal of the OPC Foundation. So OPC UA has a mapping to OPC UA pops up, of course, and it's automatic. You don't need to do anything for it. So another thing is these articles that you read, if you read closely, you'll see that they've actually compared OPC UA client-server technology to Sparkplug. Instead of comparing Sparkplug to OPC UA pops up, which is really the competing technology, and I mean, really that's an apples to oranges comparison. I wouldn't use OPC UA client-server to send data to the cloud either, right? That's why we invented pops up, right? So really, a true comparison would be comparing OPC UA pops up to Sparkplug-B, but I haven't come across these yet. Another thing is actually, the fact that Sparkplug-B is an extension to MQTT, so it only works with MQTT, versus OPC UA is actually transport protocol independent, which means that, should a customer not support MQTT for some reason, then you can still use OPC UA and its standard mapping and its standardized payload format, even if MQTT is not available. I mean, I have customers asking me for Kafka support, instead of MQTT, and that just works if, you use the OPC UA payload with a Kafka broker, right? Now, obviously, Kafka is not part of the spec yet. We're considering it, depending on how things are going with some of the other consortia that we're working with. But in general, that's an easy addition to the OPC UA spec because it is a transport protocol independent. The good news about Sparkplug, it's not all bad. The good news is that it has a defined topic mapping, right? So, using the topic tree, you can actually discover your MQTT assets, right? And that's a good thing, right? So, as you probably heard Randy talk about, 2 days ago, there's now a proposed OPC UA PubSub topic mapping for MQTT. Some folks prefer to create their own mapping, which is also totally fine. So we're probably just going to make it a recommendation rather than, a strict mapping that must be adhered to. But in general, it's a good idea to define a topic mapping, and that's clearly what was missing from PubSub, which we corrected now. And then lastly, if you're committing to Sparkplug, you're really committing to a handful of companies that have implemented it. And that's totally fine if you want to do business with those companies, but should they decide to change the Sparkplug protocol at any time, they can do that because there's no standardization process behind it. So you might be stuck with an implementation that is out of date. So let's talk about OPC UA over MQTT, which is what everybody should be talking about. So again, don't confuse it with client server. It's a totally different technology with different communication patterns. Client server is request response. MQTT uses a broker and a bunch of publishers publishing to the broker and a bunch of subscribers reading from the broker. So that is actually a fantastic technology for cloud communication, and that's why it's used there. It's been around for a long time, right? So part 14 of the spec was released in 2017. It became an IEC standard 2018. Unfortunately, not a lot of people heard about it until more recently, when the large cloud vendors all committed to supporting it. And that's why there's so much confusion in the market. But anyway, we're trying to clear that up and give you the right facts that you can make your own decisions. Microsoft has been using it from the start. Obviously, we worked on the spec in the OPC Foundation. We were the first to implement it. We were the first to have a product, the OPC Publisher, that supported it. And we're continuously improving that product, of course. It's supported by thousands of companies, right? So since OPC UA is so prevalent in the industry, standardized mappings exist. So it is super easy to support PubSub or OPC UA over MQTT. And then you have all that interoperability at your fingertips. So what does it look like? Well, here's a sample of a message, a JSON message. There's also binary encoding, but obviously you can't read it, so I've picked the JSON encoding. And again, I actually prefer the JSON encoding because, obviously all the cloud services support JSON, and you can just ingest it without having to convert it again. So here's the JSON format, and as you can see, the white pieces are mandatory, the blue pieces are optional. So you can actually compress that message payload down significantly. Because some people say, oh, JSON is chatty and too much overhead and all this. Well, you can reduce it down to the bare minimum, and then you get good performance. So we had, people always say, oh, what about the performance? Well, we have run tests with OPC Publisher, publishing 20,000 tags, OPC UA nodes, let's say, per second on a single instance. So to the cloud, mind you. So it's very efficient. And I yet have to see a customer who wants to publish 20,000 tags per second. So anyway. So here's the payload. So the important things are the message ID, the message type, because there's different message types. There's also UA metadata message, which is sent before the actual data payload from the publisher. It defines basically what the data set that you see here in this message contains, right? And it defines their names, display names, values, or not values, sorry, the types. The values then come in the actual UA data message. So some of the best practices for sending that data is the in the payload here in the middle, if you have the actual expanded node ID in there, it makes lookup of the metadata much simpler, right? So that would definitely be a recommendation. You can put in there whatever you want. You can put in the display name, for example. Some people choose that, but I think it should be the expanded node ID, and that will help you with the metadata lookup in the cloud. And another thing that you don't have to add, but it makes sense, of course, if you're building a time series, is to add a timestamp, right? So that's that would be a big improvement, obviously. Otherwise, you'll have to use the time when you ingest the message in the cloud, which, of course, there's usually a delay of up to a second, right? So you want to be a little bit more specific when trying to correlate different events that happen at the same time in your time series database. So timestamp, I would definitely recommend. And then there's two different types of encoding. There's the non-reversible encoding, which is basically just a value. And then there's the reversible encoding, which also includes the type. So in this example here, you see body is 99 and type is 6, which I think is an int. So you know how to parse the data in your time series database. But you don't have to send that information. That information is also in the metadata message. So much better would be to send the metadata message first, with all the type information, et cetera, and then just use the non-reversible encoding to save space in your cloud message. Okie dokie. So that myth, OPC UA versus MQTT, is hopefully busted. So let's talk about OPC UA versus the asset admin shell, right? So in general, we've seen through the Corona pandemic that resilient supply chains are a good idea, right? And, also, before Corona hit, the most important topic was climate change. Just because there was a pandemic doesn't mean that climate change is magically improved. We still need to fix the climate, which also means we need to calculate our carbon emissions when we're producing stuff, right? So the European Commission is actually going to put a carbon footprint mandate into a digital product passport that they're going to make law probably next year. So everybody who's producing anything and selling it in Europe will have to, adopt this digital product passport, including carbon footprint data of that product. So how do you calculate the carbon footprint of a product which has a supply chain which is, 10 vendors deep, right? You need a cross-platform communication mechanism for that. And, this is all static data, right? This is not, time series data. This is mainly static data that needs to be communicated. So the other problem is obviously not everybody's on Azure, although that would be great, right? So, as you're moving from one supplier in the supply chain to the next, how do you exchange data if they're all on different cloud platforms, right? So that is where the asset admin shell comes in. So the asset admin shell was invented by the Platform Industry 4.0, and it's a vendor-neutral asset data sharing service. It's a shell, hence the name. So it contains data from different sources. Again, it's cross-platform. It covers the full life cycle of an asset, not just, the operational piece. So it also covers, the engineering of building the asset, manufacturing the asset, then its operation, obviously, and then finally its decommissioning. There are open source implementations of the asset admin shell on GitHub. I've contributed some of those. And, you know, there's a REST interface for the asset admin shell, which is in final release candidate. It's nearing completion, available on Swagger Hub. So you can just click a button, it generates the code for you, and you can do your implementation. The actual file format for an asset admin shell is the OpenOffice XML format, which Microsoft invented, but it's a standard now. And there's a bunch of different reasons for using OpenOffice XML. It's simple. It's basically just a renamed zip file with an XML document describing the content. And again, you can put whatever you want into an asset admin shell, including but not limited to an OPC UA information model, for example, in Node-set2 file format, right? You can put in PDFs, you can put in 3D Studio Max drawings of your asset, you can put in operational data, operational manuals, bitmaps, images of the asset in question. It's basically your machine readable product website. That's the way to think about the asset admin shell. So again, when you hear all these conversations, where should we use the asset admin shell? Where should we use OPC UA? There's all sorts of arguments back and forth. Well, if you remember what the Platform Industry 4.0 actually defined many years ago, every piece, everyone has their place in the reference architecture. So this is the so-called RAMI 4.0 cube, the reference architecture from the Platform Industry 4.0. And as you can see, each standard has their place. So for the engineering piece or the engineering phase of an asset, Automation ML is the recommended standard. For the operational piece, the maintenance, you know, life cycle of an asset, it's OPC UA. And then basically when you're communicating data, so they have the ISO 95 pyramid on the Z-axis here. So it's kind of a three-dimensional architecture. You see in the connected world, right, beyond the enterprise, if you remember your ISO 95 pyramid, it's the very top. That's where the asset admin shell should be used. And that's the recommendation. But certainly not to, you know, integrate an asset admin shell into a machine. That makes no sense. So, you know, if I look at just the operational phase, because that's where OPC UA plays, the reference architecture becomes this. So as you can see, we have a manufacturer that has a factory, right? So this is called on-premises. So you have machines building a product. There's an MES that more than likely exists to control the machines that form a production line. And then when you're turning this into an industrial IT solution, you probably have an edge gateway and a cloud gateway. The edge gateway sits on-prem, the cloud gateway sits in the manufacturer's enterprise cloud. Again, this is now the connected world in the RAMI 4.0 cube. There's a separate talk right after this actually about the UA Cloud Library, so I'm not going to talk too much about the UA Cloud Library. Just know that it's an online store of OPC UA information models. So if you are using machines on the shop floor that actually have an OPC UA interface, which hopefully they will, you can upload its OPC UA information model into the cloud library and then access it for, you know, looking up the metadata of the time series data that you're sending from the shop floor to the cloud into your time series database, which is here, directly from the cloud library. How that is done, I will, well, on Azure, I can tell you how that is done in the next presentation. You probably have some sort of graph database as well, which defines your plant. Sometimes that's an OPC UA graph. I have customers using OPC UA for that. Sometimes it's something else. If you know, if you don't know what to use, come talk to me. I have a few ideas what makes sense there. But in general, if you're doing OE calculation, you need to know which machine belongs to what production line. And then you obviously have some sort of ERP database with probably all the bill of material for the products that you're building, and you have a product database, which is something that you would probably tap into for your product website, right? So then you come into the asset admin shell domain, which basically creates a repository of asset admin shells. It's a server with a web interface. Like I said, there's a REST interface now defined for it. And it queries all those databases for the information. So for example, for operational data, it queries the time series database. For product information, it queries the product database, and so on. And then you're going to need an asset admin shell client, which is probably something your customer down your supply chain. So if you're part of a supply chain, your customer will need an asset admin shell client to access the asset admin shell repository, download the asset admin shells included in it, so it knows all the data that it needs or the customer needs for example, calculating carbon emissions. And then most likely that customer will put the information into their ERP system. So basically the arrow that you see here, right, where you're loading data from the asset admin shell into the ERP system, is the same arrow you see up here, just one level down in the supply chain. And this is not just theory, this actually works. So we built a carbon reporting demonstrator in the Platform Industry 4.0 together with the Labs Network Industry 4.0, the OPC Foundation, and the Clean Energy and Smart Manufacturing Innovation Institute in the US. We wrote papers about it. We're going to show it at SPS. Obviously, SPS last year didn't happen, but we're going to show it at IoT Solution World Congress in 2 weeks in Barcelona, and then of course at Hannover Messe, both at the Platform Industry 4.0 booth and the OPC Foundation booth. So it's basically the same architecture, slightly simplified, less pieces in it. But in the case of the carbon reporting demonstrator, we had a Festo machine. That Festo machine was connected to a Festo gateway, sending OPC UA pub sub data via MQTT to a cloud gateway, in this case, Azure IoT Hub. Then we connected the Smart Innovation Platform from Sesame to it. They have their own dashboards for it. Azure Data Explorer is a time series database in this case. The UA Cloud Library was obviously integrated, and we uploaded the machine information model to the cloud library. It's a Festo didactic machine. And then the asset admin shell server queried the time series database and the UA Cloud Library for data from that particular asset, calculated its carbon report for producing, I think it was producing a plastic part, some description. So basically calculating the carbon report for producing that plastic part and making it available in an asset admin shell, which then could be downloaded using the asset admin shell package explorer, which is available online. It's free of charge, it's open source, it's an AES client, right? So what did that look like overall? Well, here's a screenshot. So this is actually data directly from this particular demonstrator. So here's the Festo didactic machine, and here's the asset admin shell that comes with it, right? So just for completeness, I also integrated an automation ML model. So this is just an example model, but you can put in your own model. And the automation ML model is actually a sub-model within the asset admin shell. It's a file, and that file is directly included in the asset admin shell. And I took the effort of actually integrating an automation ML engine into the asset admin shell server, so you could directly parse the AML file and read the automation ML information model. And then, of course, Like I mentioned, there's a submodel OPC UA, which is also a file, but in this case, it's not included directly in the asset admin shell, but read from the cloud library. And again, an OPC UA client and server was integrated, so you could parse the file. This is a noteset file, as you can see, and directly browse the OPC UA information model within the asset admin shell. So this is how an integration should work and could work. And then, of course, you have all the other pieces that, the Industrial Digital Twin Association talks about at length. I mean, for example, they have a standardized template for a nameplate or an identification. They're working on an OPC UA metadata template as well, where you get metadata about an OPC UA server, like its endpoints and what OPC UA profiles it supports, etc., etc. So that's coming, and then this can be integrated here as well. And down here on the energy model harmonized, we actually have the carbon report included, right? So again, it can be done, and this is how it should be done, in my opinion. So finally, I want to talk a little bit about some of the contributions I've recently made to the UA Cloud initiative. So you heard Stefan talking about UA Cloud really, taking off right now with all the major cloud vendors committing to supporting it. So I thought we needed open source cross-platform reference implementations for all the different pieces that are part of the cloud initiative. You already heard a little bit about the UA Cloud library. You're going to hear a lot more in the next session about it. There is obviously more than just a cloud library. So we have also what I call a UA Cloud Publisher. It's basically an easy to use PubSub telemetry publisher application that runs on the edge, on-prem. It has an easy to use user interface, and supports obviously PubSub, including metadata, messages, etc., etc. So I use a lot for testing purposes, but it's quite complete, so you can use it as a reference. Another important piece is what I call the UA Cloud Commander. It's a online command and control app for OPC UA servers. So if you want to control your OPC UA server from the cloud or any location really, the UA Cloud Commander is an important piece, and it can be completely controlled via MQTT. So you don't need anything else, just an MQTT broker somewhere in the cloud, and it can then, so UA Cloud Commander also runs on the edge, and it talks to the MQTT broker, obviously subscribes to predefined topics that you then send messages to execute commands like, read a node, read an OPC UA node, or write an OPC UA node, or call a method node on an OPC UA server. And then finally, there's a UA Cloud dashboard, which we've used extensively actually for OPC UA PubSub cloud testing purposes. So it's online. Again, it reads messages in both JSON and binary format. It parses metadata messages, so you can use it to test your PubSub implementation against. And a lot of people do that already. So all of those are available in my personal GitHub repo. There's pre-built Docker containers, so you don't even need to clone the repo or anything like that. You just run it. Just need a Docker environment to run it in, of course. And then the UA Cloud library is obviously on the official OPC UA OPC Foundation GitHub repo. So have a look at those. Maybe they're useful to you. I would hope so. And then let me know if you have any feedback or improvement suggestions. So with that, I'm at the end of my talk. So the only thing left to do is really to thank you for your for listening, really, and I wish everybody peace, especially in Europe. Thank you.
Erich, my personal applause. Thank you very much. You not only addressed a lot of questions what the audience is really confused on the market. Should I use this or that solution and technology? And you explained perfectly how everything fits together. Also, I was really impressed about your personal commitment. I just thought about if everybody on the call and who has benefits is just spending you a drink on this isn't healthy for you. So maybe you, it's not. So maybe you just, but you have a chance. You can meet Erich at the booth of the OPC Foundation during the Hanover Trade Show. He also will be part of the press conference and so on. So and maybe you just do a handshake and say a personal thank you to him. Erich, thank you very much again for your presentation. Let's introduce the next speaker, and the next speaker is again Erich Barnstedt, but also with his colleague Jonathan from Inray company. And this time it's specifically about the topic Cloud Library. This initiative has started a while ago. It has been initiated by Erich Barnstedt from Microsoft. He has been the chairperson of this group, and he was able to find a team, an international team with a lot of big brand enterprise companies to make it happen. And I'm proud that both gentlemen are giving us a dedicated update today. The Cloud Library has been released in last year, 2021. And to my knowledge, but maybe they like to correct me, it's the world's largest library of open OPC UA-based information models available, where you can search and navigate and so on. But again, let's give the attention here to the experts. Erich.
Thank you, Stefan. Yeah, it is actually the world's largest information store of information models, of digital twins, whatever you want to call them. So let's talk about the Cloud Library, where it came from, why we need it, and its adoption today. So the basics, it's a cloud-based library. It's very scalable. It runs on any cloud. It's cloud independent. In the working group, we had representatives from Google, Amazon, Microsoft, or we still do. I mean, we're still improving the Cloud Library on a continuous basis. But really, it was important to really get all the major cloud vendors together and come up with a good architecture. So again, it's using OPC UA. Obviously, it's this online store of OPC UA information models. You can upload those information models in Node-Z2 file format. It has a REST interface. It has a GraphQL interface with a spelling mistake. And it has been a joint working group defining Cloud Library together with our partner, the Clean Energy Smart Manufacturing Innovation Institute in the US, SESMI for short. Part 1 of the spec has been published last year. It's covering the architecture and use cases. Part 2 of the spec is in final review. So the review round within the OPC Foundation's Technical Advisory Council has completed. It covers the API definition, and we're nearing completion and releasing that as well. There's an open source reference implementation on the OPC Foundation GitHub, but you don't need that reference implementation if you just want to use it, because the OPC Foundation actually agreed to host an instance of it on their dime, which is great. So just go to uacloudlibrary.opcfoundation.org. You can access it today. Some of the benefits, and I talked about these before, so very briefly, obviously, in the past, when you're doing an industrial IT project, the first step was always to connect your assets, figure out the OPC UA information models from those assets, or convert to an OPC UA information model if the asset doesn't support OPC UA natively, using some of the well-known industrial connectivity software solutions out there. And then, you're basically building your analytics pipeline in the cloud as a next step. Wouldn't it be great if you could do that before connecting the assets, or even in parallel would also be a big improvement? Because usually, the connectivity piece is done by the OT folks anyway, and the cloud analytics piece is done by the IT folks, so they're waiting on each other, right? So now you can upload the OPC UA information model to the cloud library up front. The IT folks can build their analytics pipeline up front, and all you have to do is do the connectivity piece when you get around to it, right? So obviously, another big benefit of the cloud library is to see what's already out there, so you don't have to start from scratch every time you're building a new OPC UA information model. And most of the information models in the cloud library are actually VDMA companion specifications that have been defined by the experts and should be considered best practice, right? You can also use it for simulation, of course. So if you're building a new production line, you want to simulate it before you actually build it, you can download all the information models for the assets that you want to purchase, should they be available. So obviously if they're not, then you should talk to your machine builder to put them up there. And the cloud library actually verifies the information model as well during upload, so you can use it as a verification step. So what does it actually look like from an architecture point of view? So it's quite simple, actually. It wasn't that hard to make it cloud agnostic. So really, there's two different interfaces that the cloud library uses. There's a storage interface and a PostgreSQL interface, or database interface. And the default implementation of the cloud library, the way that is in the OPC Foundation GitHub repo, is for storage, we support the Azure cloud, the AWS cloud, and the Google cloud. And for the iDatabase interface, we currently only have a PostgreSQL implementation, but it is not hard to add different databases. Already mentioned, there's a REST interface. Right now it's OpenAPI compatible. There's a Swagger UI that you can call as well to try it out. And then there's a GraphQL REST interface. And again, there's two different UIs for GraphQL built into the reference implementation, the GraphQL Playground, which everybody uses, and then another one which I forgot what it's called, but it's in there, trust me. So in figures, we have currently 251 active users, which is quite significant for something so specific. We have 67 information models available, and all the VDMA companion specs that have been released are in there. So really, it's a great starting point for your next industrial IT project. In the reference architecture that I always show everyone, you can see it here. So it is used to look up metadata for time series data, which is one of the key use cases. But there's others. There are other use cases as well, and some of the adoption I'll talk about now. So first of all, obviously, SESMI, our development partner, is using it significantly in their smart manufacturing platform. They're using it as their marketplace, what they call smart manufacturing profiles, which happen to be OPC UA information models. And they're also actually building, or they are building right now, a tool that they call, sorry, one more slide on the innovation platform. So you can import the OPC UA information model directly into the platform, as you can see here in the screenshot. And the tool that they're working on is what they call the profile designer. So it's an OPC UA information model designer between you and I. And this profile designer also has the capability to load profiles or OPC UA information models directly from the cloud library. I already mentioned in the previous talk that we built a carbon reporting demonstrator, also leveraging the UA Cloud Library. So this is quite important because it's a great way to look up additional data from the assets manufacturing a product where you need to calculate your carbon footprint from. So most of the time it's energy data that you want. Sometimes an asset also has other emissions, which you can probably calculate if you had access to the OPC UA information model and a real-time telemetry stream of data as it's producing things. So obviously you need the cycle time to calculate the carbon footprint of each part that it produces. So you can say, okay, the part that it produced was in the machine for this amount of time. And that means during that time, any emissions produced, including the energy consumption and the emissions produced producing the energy it uses, need to be part of the carbon footprint of that produced asset, of course. So already mentioned in the previous talk, here's the link again. An asset admin shell server can obviously query the cloud library. So you don't need to put the whole OPC UA information model directly in the asset admin shell, but you can just add a reference to it and then download it when you're viewing and reading and parsing the asset admin shell. Another tool that integrates with the UA Cloud Library is the UA Notesite Web Viewer. I built it myself. I contributed to the Digital Twin Consortium. You can see it there on their website. It's quite popular. There's over 1 million downloads already. And it integrates with the Cloud Library. You can load OPC UA information models directly from the Cloud Library. And you can also upload OPC UA information models to the Cloud Library from the tool. So that's quite useful. And then, as I mentioned, there's also integration with Microsoft products. For example, our time series database called Azure Data Explorer, and it can read OPC UA information models directly from the Cloud Library. Azure Data Explorer uses Custo, which is a query language. It's open source. It's on GitHub. You can see it there, and it's similar to SQL. So you get this particular query here to access the Cloud Library, authenticate with it, download a particular Notesite file. In this case, it's the Festo machine information model that we use in the carbon reporting demonstrator. And then you can import the information model directly into a table, which is displayed here. As you know, then look at and then use it as a lookup for OPC UA information as your telemetry stream in OPC UA pops up format comes into that time series database. Okay, that is all I have. Jonathan, would you like to take over?
Okay, great. So firstly, a quick introduction about myself. I'm Jonathan Malessa. I'm the team lead and product owner of OPC Router, which in turn is a product of the Inray industry software GmbH. We as Inray have been developing industrial software for over 25 years, and we've focused on Industry 4.0, IoT, connectivity, and MES for all this time. We've been a long-standing OPC Foundation member and active contributors to different working groups, like, for example, the UA Cloud Library. Quick introduction to OPC Router. It's a software router with many different plugins, enabling you to communicate with a bunch of external systems and transfer data between those systems, which usually cannot communicate directly with each other. If you would like to use OPC Router, how can you deploy it? It's not only deployable to Windows systems or virtual machines, but you can also deploy it as a simple Docker container. So you're enabled to use it in Linux environments, on Kubernetes clusters, or even deployed to edge computers fairly close to producing machinery. OPC router, as the name implies, is a capable OPC UA tool. And let's take a quick look at all the OPC capabilities OPC router offers. Firstly, the UA client, of course, offers data access capabilities, including subscriptions wherever it's fitting. You can interact by reading and writing complex data types. You're enabled to call methods, consume events, and handle alarms. And all of the aforementioned capabilities are implemented in a manner that you can browse whatever you need. So there's no requirement to know any node IDs, any browse paths. You can just use a graphical browser to select whatever you need. The entire connectivity is implemented in a secure manner, of course, and it even implements some logic level handshaking to ensure data that should be transferred has been transferred and reached the target system. The OPC UA server paints a fairly similar picture, as it also enables you to offer data access, data points, which support subscriptions, complex data types, or offering methods. You can, of course, browse all those things as you know it. The connectivity is as secure as with the UA client. It implements the very same logic level handshaking. Additionally, there's the address space designer and, of course, UA Cloud Library integration. The youngest but not less mature OPC UA capabilities are PubSub. We've implemented the data reader and data writer, of course, with browsing capabilities and secure connectivity, as previously mentioned. Let's today take a look at how easily you can adopt companion specifications as a UA server. So let's imagine there's some machinery, and this machinery provides data in the form of an XML document, which is hosted on an SMB file share. And we are required to provide this data as an OPC UA server, which is compliant to the machine tool companion specification. The tool of choice, of course, is the OPC router. Let's take a quick look at how the user interface looks. On the far left column, you can see all the available plugins. So it's quite a lot and probably pretty small. But in the center, you can see a bunch of resources linked. So you have the quick start guide, knowledge base integrations, and even references to the international distributors if you require support in different time zones or languages. Let's create our UA server instance. So we are greeted with this setup screen for our instance, where we, on the right side, enter the name, the port that will be available on, sample rate, configure some security settings, and in the bottom, even user management. But let's switch to the node sets. And over here, we can import from the UA Cloud Library. And after entering the credentials from the UA Cloud Library, we can browse by default the OPC Foundation hosted instance, but you can, of course, add additional instances if for some reason or another you have to access a private instance which isn't publicly available. Built into the UA Cloud Library and, of course, this client implementation are powerful search tools and filtering, so you can't just search using the search bar, but you can also filter using the column headers. And once you've found what you need, you simply select that and confirm it with hitting OK. The client implementation of the UA Cloud Library client implemented in the UA Server plugin doesn't just pull the node set selected, but also all of the dependencies which are required to make use of the selected node set. So switching back to the address space, not only a couple of nodes have been created, but also a directory, because all of those are marked as mandatory in the node sets selected. Let's create our first machine. Let's name it machine 1 and change its type. So we can just start typing and let's search for GMS. And once we've found what we are looking for, We just select the GMS type in this case, and all the mandatory nodes for the GMS type, the entire hierarchy is created automatically, so no need to configure all of these all of these things manually. You may or may not add optional nodes as you require it for your setup, but it's perfectly usable just as it is right now. Let's take a look at the data transfer. On the left side, we have the SMB trigger, which starts the data transfer, followed by the XML so-called transfer object. And let's take a look at the configuration of the XML transfer object fairly quickly. In the center, we have the XML document, which will be parsed later on. This is just a template, and this has the contents of one exemplary XML file. I've just picked and copy pasted the contents, as this assists me in setting up the extraction XPath expressions. So as you can see, the first row, the product instance URI, is highlighted in the expressions table, and as is the XML node in the XML document in the center. So you can easily cross-reference those. But now let's add our OPC data access element and configure it. And to configure it, as mentioned earlier, we can use a tag browser, which offers visual assistance by just being able to click through the previously created address space. Within the machines directory, the machine 1, we have the identification directory, which was automatically created. And there, let's select all the nodes we would like to write to. And after all the nodes have been selected, we just confirm those and confirm the entire configuration. Now, it's simply a matter of drawing arrows from the XML element to the OPC data access element. I guess a slide got lost there. So please imagine a couple of arrows, just like from the file content of the network file access trigger to the XML document, from the individual data fields in the XML element to the OPC data access data points. And with that, the entire data transfer has been configured. So it's very easy to set up, very easy to consume knowledge which is stored in the cloud library. And by this, the network file access trigger monitors the SMB file share for any changes. Once some changes are detected, new data transfer is initiated, the XML document is read and parsed, and all the contents are written to the OPC UA server and made available compliant to the machine tool companion specification as selected earlier. So the goal was to make the data available that the machine currently provides as an XML document in a compliant manner to the companion specification. And this was done through OPC router. But of course, this is not the only thing you can source the data from, as you can cross-reference any of those and even more systems to gather data, to combine data, merge data together, to provide them as you require some additional data points for OPC UA servers, which may or may not be provided by the machine itself. So you could aggregate data from different systems together and combine those to a single OPC UA server address space. And let's take a look at the output of the joint working groups, which through the UA Cloud library is made available to a bunch of consumers. So all of the great joint working groups where industry experts are designing specifications and using their expertise to define node sets, to define relations between those data points, and to define standards or standardized node sets, standardized information models. They can use tools like the UA Node Set Web Viewer, the Unified Automation Model Export plugin, or the Sesame Profile Designer to publish the defined standardized node set informations to the UA Cloud Library, which in turn can be used by, for example, the Azure Data Explorer, the Asset Admin Shell, the OPC router, the Sesame Profile Designer, once again, maybe you in the future, or even OPC UA PubSub, as it's currently being extended, as Erich already mentioned in the previous talk, regarding linking directly to UA Cloud Library contents. That was the quick overview over how you can very easily adopt companion specifications using contents of the UA Cloud Library to empower your UA server to be companion specification compliant very easily. Thank you for your time.
Thank you, Jonathan. I'm not sure if you can activate your camera once that we can see you, the audience can see you. Maybe also if Erich is online, you can also switch on your camera, and I can thank both of you. Now we can see you. Hello, Erich. Great presentation from both of you. Thank you very much. We have not only seen the aim and the goal of the cloud library, we have also seen it already in commercial products and how it can be used. To both of you, thank you very much for that presentation. Have a good day, have a good evening, good afternoon. Thank you.
Thank you.
We are coming to the next speaker, and it's Espen Krogh from Prediktor again. He was also our keynote speaker on day one about the energy transition, but today we want, in the application day, in the architecture and success story day, we also want to learn and see where OPC UA is already used. And Espen gave us an idea that it's used in the world's largest solar panel project and also wind turbine project. So Espen, I'm really looking forward to hear these great news from you. It's your floor.
Yes, so I did have a keynote where I introduced the benefits of information models for the energy transition. And in this session, I'm going to bring two stories to you about practical usage of information models out there in live assets. So first, we will look at the benefits of large-scale deployment of OPC UA with solar PV information models across 36 solar plants with Scatec. And then after this, towards the end of the session, I will talk about the world's largest offshore wind farm and the work to create an OPC UA information model there together with Equinor. Now, first with Scatec. So Scatec is a company that has a business model to develop, build, own, and operate renewable power plants across multiple technologies. So they started with solar, but later has also acquired wind and hydro assets and put that into the general portfolios. They currently have 3.5 gigawatts in operations and under construction, and they have additionally plans and a pipeline to build additional 14.8 gigawatts within the next few years. So this company has more than 600 employees and in about 26 countries. So this is a truly global company. They have this asset here that I introduced in the keynote, Ben Ban, the world's largest solar park when built. It's in the Egyptian desert, capacity of 1.8 gigawatts. I believe Scatec operates about 400 megawatt of those. It's visible from the outer space. But Scatec has a lot more solar parks than this one across the globe. So this is the rough structure of where they're located in various geographies. So you can see all the way from South America over to Vietnam and Burma. Now, all of these solar parks and assets is organized into one coherent big enterprise architecture. So this architecture has data capture And it has a system delivered by us in Prediktor that we call Prediktor Map Gateways that takes all the captured data and reorganizes them into an information model before provisioning the data further to a centralized system, where we also have a setup that guides the central organization where the data and lets them operate all those assets remotely. But first, let's take again a look at what I mean with an information model. Here, so we have a typical site in solar PV has a set of equipment types that will be found in most solar parks. And in an information model, you can define those types and you can organize them into a structure that have the right interconnections, etc., so that you from one equipment can navigate to the other ones, etc. So this is what we have made for Scatec, an information model that is being used then across all those 36 sites. So the numbers in this enterprise is that they have 36 solar parks. There's about 2,000 point-to-point connections for equipment communication across this enterprise. So that's quite a lot. Assuring data quality is quite a challenge with so many point-to-point connections, because as you know, if you don't get the data in, the quality of the data will be bad, and then the usage of the data will be ruined. So it's important to keep all of those data streams running at all times. There are several protocols out there towards the equipment, and our system is communicating with all of those, capturing into this central gateway before reorganizing the data and pushing it forward to the enterprise. And then at the enterprise side, a total of 1.75 million signals are coming in real time. So you have the real-time values, you have the time series, and you have the alarms and events associated with those. So that's an extensive and very large set of signals, and here comes in the evident benefit of having a standardized context to organize all those signals into one coherent information structure. Yes, so the usage of this architecture in the Scatec organization can be described like this. So they have in South Africa, Cape Town, a global control and monitoring center. So they use this centralized portfolio asset management system, and they can take on more and more tasks from the local site, so that Scatec can reduce the cost out there on the site and leave the site basically to do the rudimentary maintenance tasks when needed. Then there's also an analyst organization in Oslo with Scatec, centralized, that uses a lot of artificial intelligence tools. We have a tool that we call Data Engineering Suite, where you can actually do queries from Python into an OPC UA model and take up the data directly from the OPC UA endpoint in order to do the analysis. So all data available to the analysts immediately in a rich and structured information model. And they use their favorite tools to do whatever calculations they need. And the result of that is that they will give best practice advices to the central operating center, and they will also create new algorithms based on AR and ML that will be embedded into as new functionality in the central portfolio asset management system. So all in all, this is a fundamental strategic layer for Scatec that gives them unique opportunities to further develop and enhance their operations across all sites and onboard new technologies as they come. So Scatec is actively using this in their research activities, and I've arranged so that we can look at a video footage that tells about how this system is used in a concrete research project. So, Timo, could you please run my presentation now, or the video that I sent in?
Solar energy is growing immensely fast, and it is one of the few technologies that's actually on track Still, I mean, operations maintenance is one of the key challenges to keep that going. We need to make sure these assets have a 20, 30, maybe 40-year lifetime.
Scatec, Equinor, Prediktor and IFE have since 2018 collaborated on the research project Solutions and Strategies for Operation and Maintenance of Utility-Scale Solar Power Plants. The project is funded by the Research Council of Norway through the Energix programme and aims to utilize the data collected from large-scale power plants to increase production and reduce maintenance costs.
The challenge is for anyone to be competitive, they have to find an edge. So we actually need the kind of systems that we're developing in this project for that entire industry to thrive.
The competition is getting much stronger every year. The prices are dropping, so it's about finding a way to optimize our plant efficiency and reducing the cost by analyzing and using the data that we have available from our plants.
The project brings together Scatec, a leading global renewable energy developer and operator, Equinor, an energy giant with extensive operations and maintenance experience from the energy industry on a very large scale, Prediktor, a pioneering SCADA and asset management software developer for the renewable industry, and IFE, the leading Norwegian research group on PV technology. Each solar plant generates thousands of data points, which are streamed to a Global Control and Monitoring Centre, or CMC, in Cape Town, which monitors events and ensures appropriate data quality. A team of analysts based in Oslo then work on developing new methods for data filtering and production loss detection. These methods are then used to develop actionable insights at the Control and Monitoring Centre, which in turn improves production at the site.
100 megawatt is just an abstract number. You have no idea what it really means until you actually see it and you see what a large area it covers.
There are so many data points that are being measured every second, hundreds and thousands, if not millions of data points. We are managing to automate this process.
Let the machines crunch the data and provide high-level decision support tasks to the operators.
Combining advanced data analytics with field operations, the project has developed a novel method for analyzing production losses from soiling caused by dust and dirt on the solar panels, which enables the plant operator to understand in detail which revenue losses are occurring in different parts of the plant and to plan cleaning operations accordingly. The project has also developed a method that quantifies the production losses from faults in the solar panels, which have been detected by use of drone-based thermography, and which enables the operator to easily assess which modules are causing the most significant production losses, and hence should be replaced by new panels.
So we have a very sort of direct result, a direct benefit from it in terms of how we do operations and maintenance on our plants.
So in terms of specific results from this project that I believe is valuable, I would highlight the type of algorithms that makes us understand where the losses are. Specifically, I would highlight the work that we have done in terms of understanding the effect of soiling, and not only the physical effects, but also the effects on the revenue and the financial impact.
One of the main takeaways of this project is the importance of data quality.
We have been able to lay a fundamental layer in our systems that will enable us to extract data and analyze data and present solutions to the operators. It's a competitive advantage for us going forward.
And we need companies to succeed because this is going to be the biggest thing around.
So I guess this is a solid confirmation that OPC UA with standardized information model is a strategic benefit for industrial asset owners that would like to build out assets at scale and utilize data across their assets to become more and more efficient in their operations. Okay, so that was the story about Scatec and their usage. So next is the story with Equinor. So Equinor is an international energy company committed to long-term value creation in a low-carbon future. So the purpose of Equinor is to turn natural resources into energy for people and progress for society. So they come from oil and gas and have around 2 million barrels of oil in production every day, but they are moving quite quickly and swiftly into renewables. And today they power about 1 million European homes with renewable energy. The company has about 21,000 employees in 30 countries. And as I introduced in the keynote, they have an interesting renewable assets, the Dogger Bank. This is the world's largest offshore wind farm under construction. So it's located in the North Sea, 3.6 gigawatts, and will power 5 million UK homes with their electricity demand when it's finalized. A total of 277 wind turbines is out there, each size of the Eiffel Tower. And the area it covers is about 40 by 40 kilometers, about the size of Greater London. So it's a very impressive industrial asset. But it's a bit hard for me to call it a success story yet, and I guess when we come there, Equinor will tell about this themselves, because the project is not going to be completed before 2026. So in this session, I will look at two elements. I will talk about the planned architecture using OPC UA extensively, and then also the activities we've been doing with Equinor to develop a wind information model. So first of all, the architecture. So Dogger Bank has a set of different SCADA systems and other types of plant systems that will provide information to yet again our Prediktor map gateway, a system that can consume a range of protocols, including OPC UA, and reorganize the data and put it into a standardized information model. So the Dogger Bank is structured in 3 sites, Dogger Bank A, B, and C. And all of those will provide data to that gateway, and that gateway will then provide a single endpoint with one unified and defined information model to the base field asset management system, Equinor's Omnia Cloud, and other Equinor enterprise applications. 3 subsites, about 7 different plant systems we consume data from in each subsite. So there's about 150,000 signals in each subsite. The frequency of some of them is pretty high, about 25 hertz. So in general, it's like 240,000 samples per second. And it's both time series, real-time analysis that are exposed through this, and a standardized information model. So this information model that is here has been developed by Prediktor and Equinor in collaboration. It's been based on IC standards and definitions we find there, and then mapped onto OPC UA concepts. There's also an ambition to bring in structures from the IC 81346 standard as a future extension to the information model. So a bit about the OPC UA information model being built, and what to talk about now is why create an information model in a project at all, why do we do that, etc., and how to go about to do the job, which principles was used, and what were the steps, and actually how did the process of taking out this information model actually happen. Now, the Dogger Bank project is a 9 billion British pounds, UK pounds investment. So this is a large project separated into various project phases. And the project phases right now is that all IT information structure, etc., is being set up and planned to be integrated with each other. So this phase cannot wait for consortia or work groups to conclude on information model work. So the situation where there was no existing wind information model for OPC UA resulted in that Equinor had to initiate activities to do this in the project. But the builders of this information model and Prediktor and Equinor plans to donate the result of the work to any standards group that would like to use it later. There's some benefits, though, of using or defining and crafting an information model in a project. So the assumptions you do when you create the types, etc., they are tested immediately, and you go into quite tight loops in iterations of developing the model. You can check out under that source data streams that is not properly represented in the model, or you can check out the usability of the model for applications that will consume the model. So we used a set of principles when creating this information model and base it on the other IEC standards. So I'm not going to go into each detail of the principles. The ones interested, you can read them out. But basically, this that we should prioritize to map it to pre-existing OPC UA concepts as opposed to trying to represent the other standards directly in, I would say, non-natural OPC UA ways. So that's kind of like the principles used. Try to figure out which is the best OPC UA concepts and then map them to those. And the steps. So step one is to map the underlying concepts. Often there's a conflict between the underlying standard. Like in IEC 61400, they have their own concept for units of measure, ranges, timestamp, etc. So again, using the principle that the OPC UA concept should prevail and define a mapping to those. Next one, which you do the initial work of doing that, is to create some diagrams. We use the OPC UA visual templates, and this facilitates easy communication around the model with domain experts, etc. So it's important now to get all the domain experts and their comments into this, etc., and also the application, the client application they could use and kind of like confirm that this looks good. Third step is to take the model and implement the node set XML file, and be using the excellent UA model from Unified Automation. And then often we also see that with an extensive model, it can be efficient to build a model used based on scripts and tabular data. Then the important steps is then step 4 and 5, try to map the model towards existing sources. So when we try to do this, we discover that the chosen General Electric turbines in the Dogger Bank and other equipment exposed far more data than was already part of the IEC 61400. Hence, we saw that the model should be possible to extend with potential project-specific extensions, but they then should inherit from well-defined types in the information model or the usage of OPC UA interfaces to actually solve this. And then test the model with relevant consumers, the client applications. So our experience is that many of the client applications often don't support or have the latest OPC UA concepts available, like OPC UA interfaces. So we consider to use the aforementioned OPC UA aliasing that we heard about earlier today, and also OPC UA dictionary references. The risk of using this is that clients won't be able to utilize those in the client applications. And then after the experience with both sources and consumptions, we rework the model based on these experiences and run a couple of more iterations of doing this. And eventually, after a few iterations, we believe the model is ready to be tested and commissioned to the plant. Now, since Dogger Bank is still a few years ahead before it's going live and operated, we've been fortunate to be able to test and implement the model now in a new wind farm project that Scatec has. So the information model that was created for the Dogger Bank offshore wind farm has now proven its relevance with a land-based wind farm in Vietnam in the Scatec portfolio. And again, all this data then comes into the central organizations in Cape Town and Oslo for them to be able to look at these data besides the solar PV plant data and do the same analysis, etc. they can do in order to support the local organization doing proper operations. Okay, so these were the stories. We have quite long experience now in Prediktor using OPC UA information models at scale. The first was Johan Sverdrup. That was a success story here last year. We started with that in 2016. And now we have clients that use OPC UA and information model at scale, also in renewables, besides the oil and gas assets that was told about in the last success story. So thank you. That was all from me today.
Espen, thank you very much. It's incredible to learn about this success story. And I definitely believe we will work, and we are working already to make this also a big success story, showing the world where OPC UA is successfully used and what you have done, and also all your thoughts. This is also a call for action here for the audience. If you like to share thrilling application stories and success stories, please feel free and contact us directly. Again, thank you very much, Espen. It's a pleasure for me to announce the next speaker, Mariatou from L'Oréal. I met her in person at the OPC Day in France some time ago. And when I asked her, hey, can you share that impressive presentation again here to the international audience, she immediately agreed. So thank you very much for that, first of all. She will give us an introduction on how OPC UA helped to perform the operational mechanism inside L'Oréal. Mariatou, the floor is yours.
Hi everyone, welcome on this session. I'm Mariatou Sagna-Biare from L'Oréal Operation in Global Manufacturing Department. I am leading filling and packing engineering activities for new line, for existing line, also for line for performance improvement and the digital solution implementation. So let me introduce my company. In key figures, L'Oréal is a leader in cosmetic market with over than 32 billion euro turnover. In the group, we are present in 150 countries, 88,000 employees we are, and we drive 39 different plants. Our portfolio of brands are diverse, as you can see, from luxury brand to professional product and cosmetic active brands. Now I will share with you our approach of for digital solution implementation. At the beginning of the project that we name digital transformation, we firstly frame our program initiative to be sure that we will achieve all the activities. The first aim was focus on people. For us, they are key drivers for our project. The target was to use technical leverage that we have to tackle their daily pain point. So our operator, mechanics, manager give to us a list of pain points that they face and on their daily work. Saying that, our also target was to define a clear policy regarding cyber security. When we say data management, the first thing for our point of view is to implement cybersecurity policy to be sure that everything will be under control. The second thing was to implement 4.0 architecture. This is sorry. This is for to implement all the objectives that we have, and to also clearly define the interconnection between each level. That is to say, from OT, for OT level, coming from the equipment, the sensor, and the team, to aggregate that to our all-phone 4.0 platform in the operation division, in the operation department level. The aim also was to collect data from our consumer and to aggregate that through digital solution, digital tool for our people. So as you can see, at the early stage, we defined OPC UA as a technology that we will use in the OT level, at the OT level, and also we define how through PACML how we will manage data in the software at the software part. This architecture was clearly our backbone for data aggregation and application management. So saying that, OPC UA allowed us to clearly define the game between L'Oréal side and our ecosystem of supply. This technology, as you know, allows several things, and for us, the specification that we handle is to define the requirement at the setup part, the settings as well, and also to specify access, server level for users, etc. I'm not going to describe you how OPC UA works, but it was our, in the OT level, our backbone that allowed us to standardize this OT architecture for our digital solution. As you say, in L'Oréal, we have at the line level, filling and packing line level, we have a different machine from different supplier, and also different hardware solution, PLC, HMI, stuff like that. So saying that, this OT architecture is based off our specification on data management, and we go through edge controller that allowed us to manage their data, to be sure that all the things that we aggregate to our 4.0 cloud will be smart data. And at the third time, we define our target solution for operators and technicians to be sure that we will get the performance through digital solution. We have different phases on this implementation that we describe and we follow during pilot phases. For sure, we pass through machine data collection and aggregation of the data to our L'Oréal cloud for sure. And the target was to build a dashboard for operators and technicians. I will come in detail later on. And also to build an analytics tool that will help for a performance team. How we achieve that, and I will share also the results in this part. So We are very proud to share with you the fourth application that we already deploy in L'Oréal operation worldwide. First was a set of tools called the Connected Line. Connected Line is the tools that allowed us to use data from machine equipment and to display that data, that information in real time for our operator and technician. That help them to pilot the line without any kind of stress and all the visibility on each single different machine on the line. The second one that we implement was Dashboard Light. Dashboard Light is dedicated to performance management, and the main goal is to give visibility to our performance people and our workshop team, saying that they are the manager of our different workshop in France. Linked to Connected Line, we have a tool that we call chrono analysis, based on mainly micro stoppages on machine management. This tool is really very powerful. I will go on this part later on, but is how we give visibility to our people on all the stoppages that could happen during the production phases. So track and trace is also a tool that we dedicate to quality process management on the filling and packing line. This is to say, our activity on digital solution the 2 last year was very strong to focus on our people and link to the machine data management and collection. So let me deep dive on the first main tool. This is our dashboard that we implement on filling and packing lines. This is the main view of this dashboard with all the information coming from our IT system and also coming from machine data. You have in yellow the information of as an alert that can help operator to perform the job on the line at this stage. So carton accumulation, low level, that help operator to bring all the goodies on this on the line to avoid any stoppages. The second thing that we deliver is all the messages that link to a default. When the message is in red, that means that the machine is really stopped and the operator has to solve the issue very, very quickly. The red bar and the green bar that you see below is the performance of our people hour per hour, depending the line on the line and the target of production they have. So the second tools that I'm going to talk about is chronoanalysis application. Chronoanalysis application is linked to all the microstoppages. In L'Oréal, microstoppages is a stop could happen during the shift, the production shift, from 3 seconds to 5 minutes. We collect all this information on our cloud, and this dashboard, this view is give the information on all machine status during the production. You can see in the middle roughly how our machine perform during the production, from the filler machine to the palletizer. And the important thing as well is we can get this information from the duration part to the number of stoppages that we collect. That give to the plant team, to the performance team as well, the main focus that they will have to implement, to bring performance in this line. That will support them to daily use this application, whatever it will, in the workshop or in their office. So I'm going to share with you the connected line benefits. Their benefits are very diverse. With connected line, the set of tools of real-time dashboard and chronoanalysis, we know that we will reduce microstoppages and speed losses online, definitely. And we also increase our OEE on this on the line where these tools are already implemented. And also we are let's say we know that by testimony we reduce the workload of our operator on the line. They confirm that during their 2 past year. We share also data from any devices from the line. That is the power of the 4.0. And thanks to our architecture that we implement, we can escalate very highly, very quickly this solution around the L'Oréal plant worldwide. So coming to the track and trace for quality, these tools is linked to the process of our different line. And this is the first pilot, the result of the first pilot that we perform in lipstick line. Our aim was to collect all the data, all the let's say modification that could happen in a lipstick process during the production. That help the quality team to identify quickly and with all the elements that they need to fix this, let's say, variability that could happen on the process during the production. In the first part of the string, you have the historization of this process key data, saying that could be the temperature, could be the level of filling, etc. And we use audit trail to classify this data, that information, to be sure that the process people could have all the elements in order to be sure that the quality of our product will be at the level that we require. On this application, we drive last year our first pilot, and we are going on this second phases to implement that on our different plants. So, saying that, we come to our rollout activity that we already perform. We are proud to share with you that thanks to our backbone architecture on the OIT level with OPC UA and PACML that we defined through specification, we already implement over than 4,030 different connected line, connected machine, worldwide. That is to say that we are on high activity on this 4.0 connected line path. That brings for sure advantages and good result, I can say. The first is that we identify huge team workload reduction on our different plants. And also the very good news that we unexpected on this project is we increase our OEE target from 2 to 10%, depending of the complexity of the line that we have in our plant. Really, we are very, let's say, motivated to implement this on all L'Oréal filling and packing line when needed, and for sure for the new line that we would like to implement, this connected line tool is nowadays mandatory on our plant. Coming to different features that we have, we are really, let's say, again, motivated to give features on this 4.0 tool on filling and packing line. Our aim will be to define as 5 tools, let's say, on track and trace domain linked to hygiene activity. For sure, in our line, fillers need to get data from for the hygiene team linked to CIP and SIP. The second tool will link to the environmental, our environmental target. That will be to collect all the data from machine and to aggregate them on the tools for energy consumption monitoring. Clearly, the target will be to reduce the consumption of electricity, compressed air, etc. in machines. And the third one is how we connect machine data and manufacturing execution system data to be able to be more powerful on data management on filling and packing line. That is a very ambitious program, but with our result on the first application and the tools we implement, that give us the opportunity to go further. So my last slide will be to share with you our regional experiences and our next step that we would like to have on digital solutions. We learn a lot, for sure. We learn a lot on this, on the digital solution implementation. Keywords, let's say, that I would like to raise up here is the standardization of OT architecture help us a lot to be very scalable and to be faster on tools implementation, digital tool implementation. And I can say also, I can testimony also that the OPC UA, that specification that we address to our main partners help on the rollout phases to reduce the complexity on this area. For sure, PACML is a nice contributor on this smart data aggregation. And yes, our ecosystem of machine supplier they are very involved with us on this implementation, and for sure they give us the opportunity to have to get data from their machine with the collaboration of course L'Oréal team. As well, that I say as an introduction, the cybersecurity policy that we implement in the early phases on this digital transformation program was very helpful. As a next step, I can say that we will follow our journey with OPC UA technology. Our aim will be to explore the path of we not already use is the companion specification, path. We will try with my team to focus on existing companion specification that already set up, that the foundation already set up, but we are open to develop new companion specification according our need. And also, the last thing that we would like to implement this year is a secure remote access solution to be sure that we will make the things in a proper way, the connection in a proper way with our partner. Thank you for your attention, and I remain in your proposal to answer your question if you have so.
Mariatou, thank you very much. A fantastic presentation. We always appreciate if end users are really showing the usage and the benefit of the technology. So again, this is a call to the audience here. Please share also your experience. Be open, be inspiring for others. Gentlemen, overall, thank you very much for your presentations today. Thank you very much to the audience to listen and give us a chance to present all the technology on different levels, but also on the adoption and the success stories. It was again a great day. Thank you so much for listening. Have a good morning, have a good day, or good afternoon, good evening, wherever you are in the world. Bye-bye.